given that we studied in depth the need for alternative approaches to RNNs because of the what we call as some innovative ways to arrest the vanishing gradient or the exploding gradient. So what has been suggested is what we can call as there is a pure RNN approach, which is the unadulterated conventional neural network with cycles, with loops at T. But now we have to take some alternative approaches, which are slight variations of the basic RNN, to give it memory, to give it power to deal with longer term dependencies, etc. So one of the simplest version of this which has been proposed is what is known as bidirectional RNN. So what bidirectional RNN does is it carries context in both directions so that you are not constrained by only one side backpropagation leading to the gradient problem. And this is also useful in some scenarios where it is not necessary that you are going to predict future based on past, but you can also predict, past given future. If you have some fill in the blanks or some kind of substitutions in the past to be made. So bidirectional RNN is an advancement over basic RNN where we're talking about the flow of information in two directions. The concept still holds where a particular node semantics is still going to be based on this cycle of being able to use the previous state output and the current state input both for predicting the output of the current state, which is HT is based on not just XT, but it's also based on HT minus 1. But what bidirectional LSTM does is it is a way by which you talk about two hidden layers for both directions. So what we do is we take one layer for backward propagation and one layer for forward propagation. So what we need to understand is that here we have two layers between the input and the output layer. One we call as the forward layer, another we call as the backward layer. So the way it will work is we will do once a forward propagation and another time we will do a propagation in the reverse direction, and that's how you will get the answer. So if you see, this is the expanded version of the bidirectional RNN. If you actually view one pass, which is say S0 to S1, it is very similar to what you have as a single directional RNN. And on the other hand, if you say the reverse S0 dash to S1 dash in the reverse direction, it's very similar to one direction RNN. But here we are intelligently combining both, and the way it works is the output at any point t is not just based on xt, but it is based on output of both the node at the forward layer and the backward layer at the teeth location. So again, each layer forward and backward has dependency on either the previous left node if it is the forward movement, or the previous right node if it is the reverse pass. So you see here, what we're trying to do is we're trying to create a way by which you're not constrained by one direction of guessing the weight in terms of the delta and updating weights. Instead, you're depending on both the forward and backward layer to compute a corresponding weight. So naturally, the connections here are more complex as compared to RNN, because in a conventional RNN, you would probably, let's take a teeth loop, you only have some input to the hidden layer, then hidden layer to the output layer, and there will be one from the previous node at the hidden layer to the current node, and from current node to the next node. So here on the other hand, we will have, for the same kind of single combination of xt yt, you will have a more complex interaction because of the presence of two layers. If you see from the input layer, it is going to both the backward layer and the forward layer, and same way the output layer is receiving from both the backward layer and forward layer, and within the backward layer there is propagation from previous node to the next node, and forward layer also we have propagation from the previous node to the current node. So that way you see that the memory is being carried forward in terms of forward or the backward layer, and the output of that node is computed by using both the forward and backward. So example application of such a bidirectional node, let us say he said teddy bears are on sale, and then he says Teddy Roosevelt was a great president. So Teddy, if you had only the first sentence, would not be disambiguated with presence of only he said. We may not be able to understand if the sentence refers to the president or teddy bears. On the other hand, if we had bidirectional LSTM, where each RNN, bidirectional RNN, where each cell again can be a conventional RNN like we saw, or it could be actually a more complex structure like LSTM or GRU, which we're going to see in a little while. We should be able to resolve the reference to Teddy by looking forward and then going through the backward loop by in the second pass where we're going from last word to the first word. There we will be able to resolve. Because if you look at only the forward loop, let us say he said teddy bears are on sale. So he said would not be enough to predict what the context of teddy would be if we are talking about bears, which is coming after teddy. But if you take the second pass, which is going in the reverse direction of last word to the first word, there you should be able to get the reference between bears and teddy, and you can understand the context of teddy to be teddy bears. Same way, the president Roosevelt would be referred to in the second context. In both cases, the forward pass is not good enough. So you need to understand that bidirectional RNN are one of the earliest approaches to resolve some of the issues about dependencies which are bidirectional, not necessarily from forward to backward. This does not mean that this is fully solving the problem of vanishing gradients, but it's solving a slightly different problem, which is like you're not only looking at dependencies from one direction to another. In fact, the main problem of long-term dependency is not fully solved here, because even here, if it is a very short, long-range dependency between a word which is 4 words away from teddy, it would be difficult. But bidirectional RNN is still a good idea to capture many generic application scenarios where we're talking about multiplying the applicable scenarios of RNNs to capture not only forward dependencies for predicting future from past, but also predicting past based on future, which is basically achieved by the reverse direction loop. But then imagine here where written each cell can be an LSTM or a GRU or an RNN. So this is very important because the architecture of bidirectional RNN does not say that the node which is present here, each A dash or A, is purely a conventional RNN with a T loop. It could be a complex cell like an LSTM cell, which is what we're going to cover in a little while, where an LSTM or a GRU actually handles the problem of long range dependencies by bringing slightly more complex gated phenomena of retaining memory, and solves the harder problem of vanishing gradients. But bidirectional RNN, it has its own merit, especially in scenarios like what I mentioned, where you're not just going to predict future given past, but you're also going to predict past context given future. So while I mentioned that bidirectional RNN is an alternative architecture, it is not for capturing long-term dependencies. It's mainly for making sure that we're able to capture both sides dependencies. The architectures which are responsible for capturing semantics of both directions is the main idea. Whereas the long range dependencies is captured by more complex architectures like LSTM or GRU.